In the last few lectures, we have been looking at pressure driven flows. We have completed our discussion on the Bernoulli equation and its various applications. And in the last lecture, we had started looking at the laminar flow in a pipe. So, the laminar flow in a pipe that we were considering was a steady and fully developed flow. A steady or unsteady and a fully developed flow. Okay. So, fully developed means that there is no change in the velocity in the streamwise x direction, okay, in a cylindrical pipe. We have chosen the x direction along the axis of the pipe, and the distance from the axis is the radial or r direction. So, we were considering a fully developed flow, and what that means is that there is no variation in the velocity in the x direction. Okay. However, the flow could be steady or unsteady. Okay. So, it could be a time dependent flow, and the balance equation that we were solving was the rate of change of momentum is equal to the rate of momentum in minus the rate of momentum out plus the sum of forces, all of them in the x direction. Note that momentum is a vector, and therefore, we are considering the x component of the momentum along the axis of the pipe. We do a shell balance on a differential volume between two surfaces of constant coordinate. In this case, you have two surfaces at r and r plus delta r in the radial direction. Okay. Two surfaces at r and at r plus delta r in the radial direction, where r is the distance from the axis, and along the axial direction there are two surfaces at the location x and at the location x plus delta x. Okay. So, those were the surfaces for which we are doing the differential balance. The surface area I had discussed for you. Surface at r is 2 pi r delta x, at r plus delta r is 2 pi r plus delta r times delta x. At x, the surface area is equal to the perimeter 2 pi r times the thickness delta r of this surface at the location x. Okay. At the location x, this was the surface area. Okay. And x plus delta x, the surface area was the same. The volume is 2 pi r delta r times delta x. Now, the rate of change of momentum was, of course, the change in momentum density times the volume divided by the time interval. That was equal to the momentum in minus the momentum out plus the forces. I had said that if the flow is fully developed, then the velocity is independent of x position. Therefore, the momentum entering at the location x, that is the x momentum entering at the location x, and the x momentum leaving at the location x plus delta x have to be the same. Therefore, for a fully developed flow, there is no net momentum that is entering or leaving this differential volume. There is a force. The forces are of two types. One is surface forces and the other is body forces. We did not include body forces in this balance, but it is quite easy to include. The surface forces are the pressure force at x and x plus delta x. As I had explained, the pressure always acts perpendicular to the surface. So, therefore, the force in the x direction acting on the differential volume has to be at the surfaces x and x plus delta x. At the surfaces r and r plus delta r, okay. So, if this is the differential volume, let us say this is the differential surface, right. The pressure acting in the x direction will be at these surfaces. Okay. The surfaces at r and r plus delta r, the pressure acts perpendicular to that surface, which is not in the x direction. Okay. It is not in the streamwise direction, it is in the r direction. Therefore, the forces acting in the x direction due to pressure are at the surfaces x and x plus delta x. Okay. And I had written down those forces for you. Okay. the forces due to the shear stress parallel to the surface, okay, are acting at r and r plus delta r. Okay. Okay. In this annular region, the forces acting in the x direction at the surfaces, the cylindrical surfaces, are at the locations r and r plus delta r, okay, as shown by these forces here. Okay. At the surface at r, the outward unit normal is in the r direction. Therefore, the stress is tau x r, okay, where tau x r is the force per unit area in the x direction acting at a surface whose outward unit normal is in the r direction. The force at the surface at r plus delta r, the outward unit normal is in the r direction. Therefore, the force is tau x r. At the inner surface at r, the outward unit normal to this annular volume is in the minus r direction. Therefore, the force is minus tau x r. Okay. And we had put both of these together here, okay, and got a balance equation. Okay. The final equation that we got was partial of rho Vx by partial t is equal to minus partial Vp by partial x plus 1 by r d by dr of r tau x r by partial r plus any force Fx in the x direction. Okay. And the stress was mu into partial Vx by partial r. Okay. So, that is the equation for the stress and the unsteady momentum balance equation for the x momentum, okay, for a fully developed flow. Okay. So, and I had also made an argument for you that the pressure gradient has to be linear in x. Okay. If I take the momentum balance equation and take the derivative of that with respect to x, okay, if I take d by dx, okay, of this entire momentum balance equation, okay, and interchange the order of differentiation, which can be done because r, t and x are all independent coordinates, then I find that the second derivative of the pressure with respect to x has to be equal to 0. What that means is that the first derivative has to be a constant, okay, or the pressure gradient has to be a constant. The pressure has to vary linearly with the x direction. Okay. It has to decrease linearly in the x direction. Okay. So, therefore, in the subsequent analysis of a fully developed flow, we will assume that dp by dx is equal to a constant. Okay. Partial p by partial x is independent of x, okay, and it is independent of r, okay, because we showed that if you write the momentum balance for the r direction, you get dp dr is equal to 0. Okay. So, it is independent of r and dp by dx is independent of x. It could be a function of time for unsteady problems. We will see that when we come to looking at time dependent flows. Okay. So, I have got the equation for you for rho partial Vx by partial t is equal to 1 by r, let me write, plus Fx. Okay. That is the momentum conservation equation, and p is independent of r. So, first let us consider steady flows. Okay, in the absence of any forces. Okay. So, in that case the time derivative is 0 and this Fx is equal to 0. Okay. If there are no body forces and if the flow is steady. Okay. And we know that dp by dx is a constant for a steady flow. Therefore, this since p is not a function of r and for a steady flow p cannot be a function of time, this implies that the partial derivative is the same as the total derivative, okay, because we know that for from the momentum conservation equation we know that the second derivative is 0. That means dp by dx is independent of x, okay, and it is independent of r, okay, and it is independent of r from the momentum conservation equation in the r direction, okay. Because of that, this derivative dp by dx, what I will call the pressure gradient, is independent of r and it is independent of x. In addition, if the flow is steady, then this dp by dx is also independent of time, okay, and therefore it is a constant, okay. It is equal to the total derivative because it is also independent of time, okay. And the velocity Vx we already know is independent of x for a fully developed flow. It is independent of the downstream coordinate because the flow is fully developed, and the profile is the same at all axial locations. For a steady flow, this is also independent of time, okay. So, the equation reduces to 0 is equal to minus dp by dx, okay, plus, okay, for a constant viscosity system this is equal to mu by r d by dr of r dvx by dr, okay. Total derivatives here, because Vx depends only upon r, it is independent of x. P depends only upon x, it is independent of r, and the derivative is a constant. Note that dp by dx has to be negative if Vx is positive, okay. So, if I have a pipe flow, okay, if the velocity is in the plus x direction, if the velocity is in the plus x direction, that means that the pressure in the inlet is higher than the pressure in the outlet. So, if I plot the pressure as a function of x, this has to be a linearly decreasing function, okay, which means that dp by dx has to be negative, okay. Okay, the constant, it is a constant pressure gradient. The pressure is decreasing with downstream distance, and therefore dp by dx is negative, okay, in this particular case, okay. So, we can solve this mu by r d by dr of r d, okay. Let me just solve for the stress first, okay. So, is equal to dp by dx, okay. And I can integrate this once to get r tau x r is equal to r square by 2 mu dp by dx plus some constant, okay. I just multiply throughout by r by mu and integrate once, and I will get tau x r is equal to r by 2 mu dp by dx plus a constant, okay, constant of integration. That constant of integration is determined from the condition that the stress has to be equal to 0 at r is equal to 0, okay. Okay. The reason for that is as follows. We know that tau x r is equal to mu dvx by dr, okay. And if you recall, when we did the problem of heat conduction in a cylinder, okay, I had told you that for heat conduction in a cylinder, the radial coordinate varies from 0 to 1, okay, the scale radial coordinate. In this particular case, it varies from 0 up to the pipe radius r, okay, that is the extent of the radial coordinate. Therefore, we have to have boundary conditions at r is equal to 0 and r is equal to r. At r is equal to r, we know that there is the no slip condition for the velocity. The velocity has to be at the wall of the pipe has to be equal to 0 from the no slip condition for the velocity. What about at r is equal to 0? If you recall, we had derived a symmetry condition, okay, if the velocity profile or the temperature profile looks something like this and it is axisymmetric, okay, and it is axisymmetric, then the velocity profile from the other side has to look something like this, just from symmetry. Okay. Similarly, from all other directions, the slope of the velocity profile will be equal to 0, will be non-zero at the axis at r is equal to 0. Okay. And this leads to an unphysical cusp at the axis, because you cannot have the derivative being different depending upon which direction you are approaching the center from. The derivative of the velocity profile, there is no physical boundary at r is equal to 0, and the derivative will be continuous only if the derivative is 0, okay, at r is equal to 0. Okay. That is the only way that you can get a uniquely specified value for the derivative regardless of the direction that you approach the axis from. Okay. And therefore, this tau xr has to be equal to 0, okay, or mu dvx by dr has to be equal to 0. Okay. The shear stress has to be 0 at the axis, or the velocity gradient has to be 0 at the axis, and therefore, the velocity profile has a maximum at the axis. Because there is no physical boundary there, the derivative will be uniquely specified regardless of the direction that you approach the axis, only if the derivative is 0 at the axis. And therefore, this constant has to be equal to 0. Okay. Tau xr is equal to 0 at r is equal to 0 implies this constant is equal to 0. Now, the wall shear stress tau w is equal to the value of tau xr at r is equal to r, okay, where r is the radius of the pipe, okay, where r is the radius of the pipe. And so, this is equal to r by 2 dp by dx. Okay. Note that dp by dx is negative. So, this implies that the wall is exerting a negative force on the fluid. Okay. The wall is exerting a force on the fluid in the negative x direction. The fluid is actually exerting a force in the positive x direction on the wall. Okay. The negative force exerted by the wall on the fluid is equal to the difference in pressure times the area. Okay. And the magnitude of the wall shear stress is equal to r by 2 into minus dp by dx, because as we know dp by dx is negative. Okay. Okay. So, now we have mu dvx by dr is equal to the shear stress is equal to my apologies, I made a mistake here. So, there should be no viscosity in the expression for the stress. The stress is just 1 by r d by dr of r times tau xr. Okay. Okay. As shown over here, there is no viscosity in the expression for the stress. The viscosity comes in the expression for the relation between the stress and the velocity gradient. So, this is equal to minus dp by dx into minus r by 2. Okay. And this you divide throughout by mu and you integrate one time to get Vx is equal to minus r square by 4 mu dp by dx plus some constant. Okay. So, that is the velocity Vx as a function of r. Okay, there is the velocity Vx as a function of r. The constant is determined from the condition that at r is equal to r, Vx is equal to 0. Okay. At the wall of the pipe, the velocity is equal to 0. Okay. And what that implies is that c is equal to r square by 4 mu. Okay, so, Okay. Okay. There is a negative sign on both of these. Okay. Note that minus dP by dx is a positive quantity. That is the reason that I have retained a negative sign on the pressure gradient dP by dx. Okay. So, this is equal to r square. Okay. So that the velocity Vx is equal to 0 at r is equal to r. Okay. It satisfies this condition. Okay. And finally, I get the expression for the velocity Vx. Okay. Minus dP by dx 1 by 4 mu into r square minus r square. Okay. So, this is the velocity Vx, a parabolic flow in a pipe. I can write this in terms of the maximum velocity. Okay. I can write this as V max into 1 minus r square by r square. Okay. So, that the velocity is equal to V max at r is equal to 0. Okay. Where V max is equal to minus r square by 4 mu into minus dP by dx. Okay, that is the expression for the maximum velocity, where V max is the maximum velocity at r is equal to 0. Okay. At the center, r is equal to 0, V is equal to V max. What is the average velocity? Okay. The average velocity is equal to the cross sectional area times the flow rate. So, let us calculate the flow rate first. Okay. The flow rate V dot, volumetric flow rate. Volumetric flow rate is the flow of volume of fluid per unit time that is flowing through the pipe. This is equal to the integral over the pipe radius of r d of 2 pi r dr times Vx. Okay. So, if you look at the pipe cross section, if I take a differential volume of thickness, a differential cross sectional area of thickness delta r at the location r. Okay. If I take a differential cross sectional area of thickness delta r at a radius r from the axis, then the area is going to be equal to the perimeter 2 pi r into delta r. Okay. So, that is the differential cross sectional area. If I multiply the differential cross sectional area by the velocity Vx at r and integrate over r, I will get the total flow rate. Okay. So, that is what I have done here. This is the differential cross sectional area 2 pi r dr multiplied by Vx integrated over the entire cross sectional area. Okay. That gives me the volumetric flow rate. Okay. So, this is going to be equal to 2 pi integral 0 to r dr V max into 1 minus r by r. So, let me use the pressure formulation, into 1 by 4 mu into r square minus r square. Okay. So, you can see that I can take this first term outside because it is all a constant, okay, and the equation will be equal to pi by 2 mu integral 0 to r dr into r square minus r square, okay, into, I am sorry, I have not got the dp dx out. And you can evaluate this quite easily, and the volumetric flow rate turns out to be equal to minus pi r power 4 by 8 mu dp by dx. This is the volumetric flow rate. The average velocity is equal to the volumetric flow rate divided by the cross sectional area. Okay. Is equal to minus r square by 8 mu dp by dx. Okay. That is going to be equal to the average velocity. Okay. Recall that the maximum velocity, okay, we had calculated it here. Okay. The maximum velocity is equal to minus r square by 8 mu dp by dx. This implies that the average velocity, the maximum velocity is equal to 2 times the average velocity. Okay. The maximum velocity at the center of the pipe is equal to 2 times the average velocity. Okay. And we had also got an expression for the wall shear stress here. Okay. We had also got an expression for the wall shear stress here. Okay. The wall shear stress is equal to, okay, tau w is equal to minus r by 2 dp by dx. Okay. This was the wall shear stress. Okay. So, there is a, yeah. Okay. So, that is the magnitude of the wall shear stress, r by 2 times dp by dx. Okay. So, now we can calculate the friction factor. F is equal to tau w by rho V average square by 2. The ratio of the wall shear stress and the kinetic energy per unit volume. Okay. And you substitute for the average velocity and the wall shear stress. Okay. So, in the numerator you will have minus r by 2 dp by dx. Okay. So, I will just take the magnitude of dp by dx. Okay. So, you get a positive quantity. Okay. Divided by rho V average by 2, okay, into V average, which is equal to r square by 8 mu into dp by dx. Okay. That is the average velocity. Okay. And I have taken one value of dp by dx over here. Okay. So, okay, I can cancel out the dp dx in the numerator and denominator. Note that while simplifying this term here, okay, I have kept one rho average, rho times V average a constant, and the other one I am simplifying it here. Okay. So, you can see that this r will cancel out, okay, with one r here, these two will cancel out, okay, and if I simplify this I will get 8 mu by rho V average times R. Okay, that is the expression for the friction factor. And I substitute that the radius is equal to the half the diameter. Okay. The radius of the tube is equal to half the diameter, because the friction factor is usually expressed in terms of the diameter, not the radius. So, you will get 8 mu, I am sorry, 16 mu by rho V average times the diameter, okay, which is actually 16 by Re. Okay. 16 by Re is the correlation for the friction factor for the laminar flow in a pipe, where the Reynolds number is equal to rho V average times d by mu. Okay. So, I have derived for you the friction factor correlation for the laminar flow in a pipe. So, this was done by just solving the momentum balance equation at steady state. Okay. The momentum balance equation at steady state for the shear stress, and then the velocity profile with the 0 slope condition at the center, because the velocity has to go through a maximum. And we found that the maximum velocity is 2 times the average velocity from the flow rate calculation. And then from the wall shear stress, we found out what is the friction factor. So, this is the friction factor in a pipe. I will continue this a little bit in the next lecture, say a few more things about this pipe flow before we go on to dealing with a concrete example, okay, how this pipe flow, this friction factor formulation can be used for predicting the volumetric flow rate in a pipe. So, I will continue this in the next lecture. I will see you then.